Thousands of years ago, our ancestors looked up at the night sky and wondered what existed beyond the stars. They built giant monuments, studied the movements of planets, and tried to understand our place in the universe. Today, NASA continues this same journey of discovery, but with tools our ancestors could never have imagined. From the first missions that took us to the moon, to modern telescopes that capture light from galaxies so distant it took billions of years to reach us, each discovery reveals something new and surprising about the cosmos. In this relaxing journey of more than 2 hours, we will explore the most incredible discoveries from the space agency, from ice-covered planets at the edge of the solar system to giant black holes at the center of distant galaxies. We will learn about moons that may harbour hidden oceans, nebulae where new stars are born every day, and phenomena so strange they challenge everything we thought we knew about reality. Each discovery is a piece of the giant puzzle that is our universe, and NASA has shown us that the more we learn, the more we realise how much there still is to discover. Subscribe to the channel, leave your like and comment from what part of the world you are watching, get comfortable and relax. Let's begin. Thousands of years ago, long before cities spread their light across the night, long before telescopes turned their gaze toward distant stars, our ancestors stood beneath the same sky we see tonight and wondered. They had no instruments, no equations, no photographs beamed back from spacecraft millions of kilometers away. They had only their eyes, their minds, and an overwhelming curiosity about the points of light that moved slowly against the backdrop of stars that did not move at all. They watched the moon wax and grow full, then fade again into darkness. They tracked the wandering planets as they traced their paths across the constellations. They saw comets blaze across the heavens and wondered if they were omens or messages from something beyond their understanding. And in that wondering, in that deep human need to know what lies beyond the horizon of our world, the story of space exploration was already beginning. It would take thousands of years, countless lifetimes of observation and thought before we would build machines capable of leaving Earth's surface and traveling into the void. But the spark was there from the start, burning quietly in the mind of every person who looked up and asked what if, burning in the heart of every culture that built monuments to track the movements of celestial bodies, burning in the questions that had no answers yet but refused to be forgotten. Tonight, as you settle into this quiet space, as your breathing slows and your thoughts begin to drift, we are going to follow that spark forward through time. We are going to trace the long arc of human curiosity from those ancient observers to the modern space agency that continues their work today, but with tools and knowledge they could never have imagined. NASA, the National Aeronautics and Space Administration, is the inheritor of that ancient tradition of watching and wondering. For more than 6 decades, it has sent machines and people beyond our atmosphere to explore the solar system and the universe beyond. It has landed rovers on Mars and probes on distant moons. It has photographed galaxies so far away that their light has travelled for billions of years to reach us. It has measured the temperature of planets, analysed the composition of asteroids, and listened to the echoes of the Big Bang itself still reverberating through space. Every discovery, every photograph, every measurement is another piece of the puzzle, another step toward understanding not just what is out there, but what we are, where we came from, and whether we are alone. This is not a story that demands your full attention. You do not need to memorize facts or remember names. You do not need to solve equations or visualize complex diagrams. This is a story meant to wash over you gently, like waves on a distant shore, carrying you softward into rest while filling your mind with images of vast nebulae, frozen moons, and galaxies spinning slowly in the darkness. If you drift away before the story ends, that is exactly as it should be. If your thoughts wander to the stars and then to dreams, you are following the same path humans have walked for millennia. So let your body relax, let your muscles release the tension they have been holding, let your breathing deepen and slow, and as you listen, let yourself float upward in your imagination, rising above the room where you lie, above the city or countryside around you, above the clouds and the thin blue shell of atmosphere, out into the darkness where Earth becomes a small blue marble suspended in an ocean of night. This is where the story truly begins, not on the ground where we stand, but in the space between worlds, in the vast distances that separate one point of light from another, in the silence that surrounds everything and the mysteries that silence science contains. From the very beginning, humans have been builders of tools. We shaped stones into blades, wood into shelters, fire into warmth and protection. But some of our earliest and most enduring tools were not made for hunting or building. They were made for measuring the sky. In ancient Mesopotamia, astronomers tracked the movements of Venus and recorded them on clay tablets, creating some of the first written records of systematic observation. In Egypt, the alignment of pyramids reflected careful study of the stars, their passages marking not just directions on Earth, but the passage of time itself. In Central America, the Maya built elaborate observatories and developed calendars of remarkable precision, predicting eclipses and planetary alignments with accuracy that would not be surpassed for centuries. In China, astronomers recorded supernovae, comets, and meteor showers in detailed chronicles that still provide valuable data to modern scientists. Across the Pacific, Polynesian navigators learned to read the stars so well they could cross thousands of kilometers of open ocean without instruments, guided only by their knowledge of the sky and the patterns of wind and wave. All of these cultures, separated by vast distances and developing independently, turned their attention upward and asked the same fundamental questions. What are these lights? Why do they move the way they do? Is there meaning in their patterns? Can we predict what they will do next? And beneath all those questions was an even deeper one, the question that still drives space exploration today. What is our place in all of this? For most of human history, the answers to these questions were bound up with mythology and religion. The heavens were the realm of gods and spirits, and the movements of celestial bodies were expressions of divine will. But slowly, carefully, some observers began to notice that these movements followed patterns, that they could be predicted, that the universe operated according to rules that could be understood. This shift from mythology to science was gradual and not always welcomed. It took courage to suggest that the Earth was not the center of the universe, that the stars were not small lights embedded in a nearby sphere but distant suns in their own right, that the Milky Way was a vast collection of stars, and that our solar system was just one small part of it. Each of these revelations expanded our sense of scale and diminished our sense of centrality, and each was met with resistance before eventually being accepted as the evidence became overwhelming. By the time the 20th century began, we had learned an enormous amount about the universe through observation alone. We knew that planets orbited the sun, that stars were distant and varied in size and temperature, that galaxies existed beyond our own, and that the universe was far larger and older than anyone had previously imagined. But we were still bound to Earth's surface, still limited to watching from the bottom of our atmosphere, looking up through air that blurred and distorted the light reaching us from space. The dream of leaving Earth, of travelling beyond the atmosphere to see the universe more clearly, had existed for centuries in fiction and imagination, but it remained only a dream until the middle of the 20th century, when a combination of scientific understanding and technological capability finally made it possible. The space age began not with NASA, but with the Soviet Union's launch of Sputnik 1 in 1957, a small metal sphere that did nothing but circle Earth and broadcast a simple radio signal. That signal, a steady beep that could be picked up by amateur radio enthusiasts around the world, announced that humanity had finally succeeded in placing an object in orbit around our planet. The age of space exploration had begun. In response, the United States created NASA in 1958, bringing together engineers, scientists, and dreamers who shared a common goal to explore space, to understand what lay beyond our atmosphere, and to push the boundaries of what was possible. From the beginning, NASA's mission was as much about knowledge as it was about competition or national prestige. Yes, the space race between the United States and Soviet Union drove much of the early exploration, but beneath that competition was genuine curiosity, a desire to answer questions that had been asked for thousands of years. What does the surface of the moon look like up close? What are the other planets made of? Are there other worlds where life might exist? And perhaps most fundamentally, can humans survive and travel in space? Or are we forever bound to the one world where we evolved? These questions shaped the early decades of space exploration, and they continue to guide NASA's work today. In the years since that first satellite was launched, we have sent humans to the moon and brought them safely home. We have landed machines on Mars, Venus, and Titan. We have flown past every planet in our solar system and sent probes beyond the edge of the sun's influence into interstellar space. We have built telescopes that can see galaxies forming in the early universe, and we have discovered thousands of planets orbiting other stars. Each mission, each discovery, has expanded our understanding and raised new questions. The universe, it turns out, is far stranger and more wonderful than anyone imagined. And this is where you are now, lying quietly in the present moment, connected by an unbroken thread to those ancient observers who stood beneath the same stars and wondered. The technology has changed, but the questions remain. What is out there? How does it work? What does it mean? And in seeking answers, we find not just facts and data, but something deeper. We find perspective. We find humility. We find a sense of connection to something vast and ancient, something that was here long before us and will continue long after we are gone. As you listen tonight, you are part of that long tradition of curiosity and wonder. You are, in your own quiet way, an explorer, allowing your mind to travel to places your body cannot go, imagining worlds you will never touch, contemplating scales of time and distance that exceed all ordinary experience. And as you drift towards sleep, carried on these thoughts of distant worlds and cosmic mysteries, you are doing exactly what humans have always done. You are wondering. You are reaching out with your imagination toward the unknown. You are asking what if, and that question, asked billions of times across thousands of years, is what brought us from wondering about lights in the sky to walking on the moon, from scratching observations on clay tablets to photographing galaxies billions of light years away. So rest now. Let your mind wander among the stars. Let yourself feel small in the best possible way, small but connected, temporary but part of something eternal. The universe is vast beyond comprehension, but you are here in it, thinking about it, marveling at it, and that simple act of wonder is itself a small miracle, a brief flowering of consciousness in an ocean of space and time. The discoveries are waiting, spread out before us like treasures scattered across the cosmos, each one a gift of knowledge hard-won through decades of effort and ingenuity. We will explore them together, gently, without hurry, allowing each revelation to settle softly into your thoughts before moving on to the next. And if sleep comes before the journey ends, that is perfectly fine. The universe will still be there tomorrow, still vast, still mysterious, still waiting. The moon has always been our closest companion in space, a constant presence in the night sky that has inspired poets, guided travelers, and marked the passage of time for as long as humans have existed. But until the middle of the 20th century, it remained as untouchable as the stars themselves, a distant world that we could see but never reach. That changed on July 20th, 1969, when two astronauts descended from lunar orbit in a fragile spacecraft, guided by computers less powerful than a modern smartphone, and set foot on another world for the first time in human history. The Apollo 11 mission, and the 10 missions that preceded it in preparation for that moment, represented one of the greatest achievements in human history, not because it was easy, but because it was extraordinarily difficult and we chose to do it anyway. Getting to the moon required solving thousands of problems that had never been solved before. How do you build a rocket powerful enough to escape Earth's gravity while still light enough to be practical? How do you navigate across hundreds of thousands of kilometers of space with enough precision to hit a target that is constantly moving? How do you keep astronauts alive in an environment where there is no air, no protection from radiation, and temperatures that swing between extremes depending on whether you are in sunlight or shadow? How do you design a spacecraft that can land on a surface no human has ever touched and then launch again to return home? Each of these problems required innovation, creativity, and careful engineering. Thousands of people worked on different aspects of the challenge, each one contributing their expertise to a project that was, in many ways, as much about cooperation and coordination as it was about technology, and in the end, they succeeded. Neil Armstrong and Buzz Aldrin spent just under a day on the lunar surface, collecting samples, taking photographs, and conducting experiments, while Michael Collins orbited above them, maintaining the spacecraft that would carry them home. The images they brought back transformed our understanding of the moon and our sense of what was possible. Before Apollo, the moon was a mystery. We knew it was a rocky body with no atmosphere, that its surface was marked by craters and dark plains that ancient astronomers had mistaken for seas. But we did not know what it would feel like to stand there, to see Earth hanging in the black sky, to walk in gravity only 1/6 as strong as what we experience on our homeworld. The astronauts described the lunar surface as desolate but strangely beautiful, a landscape of grey dust and sharp-edged boulders under a black sky where stars were visible even during the lunar day. The dust clung to everything, fine as powder, but rough enough to wear through the fabric of their spacesuits if they were not careful. When they walked, their footprints pressed into the surface with perfect clarity and remained there, undisturbed by wind, because there is no wind on the moon, no weather, no erosion, except the slow, patient work of micrometeorites that have been sandblasting the surface for billions of years. Those footprints are still there today, more than 50 years later, looking exactly as they did the moment they were made, a testament to the permanence of the moon's silence. The rocks they brought back told an even more profound story. By analysing these samples, scientists learned that the moon is not a separate world that was captured by Earth's gravity, as some had theorised, but was created in a catastrophic collision early in our solar system's history, when a Mars-sized object struck the young Earth and threw an enormous amount of material into orbit, material that eventually coalesced into the moon we see today. This means the moon is, in a very real sense, a part of Earth, a piece of our world that was torn away in violence and has been circling us ever since, a permanent reminder of the chaotic forces that shaped the planets billions of years ago. The Apollo program continued after that first landing. 5 more missions successfully landed on the moon, each one exploring different regions and bringing back more samples. Apollo 15, 16 and 17 carried a lunar rover, a small electric vehicle that allowed astronauts to travel several kilometers from their landing site and explore a wider range of terrain. They collected rocks from the highlands and the lowlands, sampled soil from different depths, and set up scientific instruments that continued to send data back to Earth long after the astronauts had left. These instruments measured moonquakes, detected the thin wisp of atmosphere that clings to the lunar surface, and recorded the impact of meteorites as they struck. All of this data helped scientists piece together the moon's history, a history that is also, in many ways, Earth's history. But perhaps the most profound impact of the Apollo missions was not scientific, but philosophical. For the first time, humans could look back at Earth from another world and see it as it truly is, a small, fragile sphere of blue and white suspended in darkness, the only home we have ever known floating in an incomprehensibly vast universe. The photographs taken during the Apollo missions, particularly the famous Earthrise image showing our planet rising above the moon's horizon, changed how we think about ourselves and our world. They revealed that borders and nations, which seem so important and permanent from the ground, are invisible from space, that the atmosphere that protects us is thin as a whisper, that Earth is not the centre of a cosmic drama, but a tiny stage on which all of human history has played out. This perspective, sometimes called the overview effect, has been described by almost every astronaut who has experienced it as deeply moving and transformative, a moment when the intellectual knowledge that Earth is a planet becomes visceral, emotional truth. After the Apollo program ended in 1972, no human has returned to the moon. The reasons are complicated, involving politics, economics, and changing priorities, but the absence is striking. For 3 years, humans walked on another world, and then we stopped. The footprints remain. The flags planted by each mission still stand, though the sun's radiation has likely bleached them white by now, and the scientific instruments gradually fell silent as their power sources degraded. The moon returned to being a place we visit only with robotic probes, watched from a distance, always present but no longer touched. Yet, the legacy of Apollo extends far beyond those 12 astronauts who walked on the lunar surface. The technology developed for the moon missions found applications in medicine, computing, materials science, and countless other fields. The sense of possibility it created inspired generations of scientists and engineers, and the knowledge gained continues to inform our understanding of how rocky planets form and evolve. In recent years, interest in returning to the moon has grown again. NASA's Artemis program aims to land humans on the moon once more, this time with the goal of establishing a sustained presence, a lunar base that could serve as a stepping stone for missions deeper into the solar system. Robotic missions from multiple countries have mapped the moon in unprecedented detail, discovering water ice in permanently shadowed craters near the poles, resources that could be used by future explorers. The moon, it turns out, is not as dead as it appears. It has secrets still to reveal, resources that might be useful, and lessons that could help us learn to live on other worlds. But even if we never return, even if the footprints left by Apollo remain the only marks of human presence on another world, the achievement stands. For a brief moment in history, humans looked at the moon, not with longing or wonder, but with determination, and they found a way to go there. They crossed the vast gulf of space that had separated us from every other world since our species first looked up at the night sky. They planted flags and collected rocks and looked back at Earth from a perspective no one had ever had before. And in doing so, they proved that the ancient dream of travelling beyond our world was not just fantasy. It was difficult, dangerous, and expensive. It required the combined efforts of thousands of people and the resources of an entire nation. But it was possible. And if it was possible to reach the moon, then perhaps, with enough time and effort, it might be possible to reach even further. As you rest now, imagine standing on that dusty grey surface, the Earth hanging above you in a black sky, alone in a silence so complete that you can hear your own heartbeat echoing inside your helmet. Imagine the sense of isolation and connection existing simultaneously, farther from home than any human has ever been, yet still tethered by radio waves and shared purpose to everyone you left behind. Imagine looking at the stars without atmosphere to dim them, seeing them sharp and steady, not twinkling but burning with a clarity impossible to experience from Earth's surface. Imagine knowing that your footprints will outlast empires, that in the absence of wind and rain they could remain visible for millions of years, long after every trace of human civilization on Earth has eroded away. The moon is waiting there still, exactly as the Apollo astronauts left it, silent and patient and marked forever by their presence. It circles Earth every night, going through its phases as it has for billions of years, sometimes full and bright, sometimes a thin crescent, sometimes hidden entirely in the shadow of our world. And if you look up at it tonight, or tomorrow, or any night in the future, you can know that humans once walked there, that the dream of reaching beyond our world has already been achieved once and could be achieved again. The moon is no longer impossible, it is simply distant, and distance, as we have learned, is something that can be crossed. Beyond the moon, beyond the inner planets of Mercury, Venus, Earth, and Mars, the solar system changes character completely. Out there, beyond the asteroid belt that marks an invisible boundary, the worlds become strange and cold, giant planets made mostly of gas and ice, accompanied by families of moons that are worlds unto themselves, some of them larger than the planet Mercury, each one a unique environment shaped by forces we are only beginning to understand. This is the outer solar system, a realm that remained mysterious and largely unknown until NASA began sending robotic explorers to visit these distant worlds in the 1970s. The first missions to the outer planets were the Pioneer and Voyager spacecraft, small robotic probes launched with no expectation of return, designed to fly past the giant planets, gather data for a few hours or days as they swept through each system, and then continue outward into the darkness beyond. These were one-way journeys, missions of pure exploration, undertaken with technology that seems primitive by modern standards, but represented cutting edge of what was possible at the time. The spacecraft carried cameras to photograph the planets and their moons, instruments to measure magnetic fields and radiation, and sensors to detect particles and cosmic rays. And because they were traveling too far from Earth for real-time control, they were programmed to make many decisions autonomously, adjusting their cameras and instruments according to what they encountered. It took years for these spacecraft to reach their targets, years during which the small team of scientists and engineers who built them could only wait and hope that everything would work when the time came. And remarkably, it did. Voyager 1 and Voyager 2, launched in 1977, took advantage of a rare alignment of the outer planets that occurs only once every 176 years, using the gravity of each planet to accelerate toward the next in a cosmic game of billiards that allowed them to visit Jupiter, Saturn, Uranus, and Neptune in a single extended mission that became known as the Grand Tour. The images they sent back transformed these distant worlds from points of light in telescopes to real places, each one unique and far stranger than anyone had anticipated. Jupiter, the largest planet in our solar system, revealed itself as a churning mass of clouds organized into bands and swirls, dominated by the Great Red Spot, a storm larger than Earth that has been raging for at least 400 years and possibly much longer. The Voyager spacecraft discovered that Jupiter has a faint ring system, thin and dark. Nothing like Saturn's spectacular rings, but evidence of the same processes at work. They photographed Jupiter's largest moons in detail for the first time and discovered that these moons were not simply dead balls of rock and ice, but active, complex worlds. Io, the innermost of the large moons, turned out to be the most volcanically active body in the solar system, its surface constantly being resurfaced by eruptions of molten sulfur and silicate rock driven by the tidal forces of Jupiter's immense gravity. Europa, the next moon out, showed a surface of smooth ice crisscrossed with cracks and ridges, very few craters, indicating that the surface is young and still changing, hiding beneath it what scientists now believe is a global ocean of liquid water kept warm by the same tidal forces that heat Io's interior. Ganymede, the largest moon in the solar system, showed a surface divided between ancient dark terrain and younger, brighter regions of grooved and ridged ice. And Callisto, the outermost of the large moons, revealed itself as one of the most heavily cratered objects in the solar system, a record of billions of years of impacts preserved in ice. Each of these moons became not just a name, but a place, a world with its own story, its own mysteries. When the Voyager spacecraft continued on to Saturn, they found a planet of breathtaking beauty, its ring system far more complex than anyone had realized, composed of thousands of individual ringlets, some braided together, some showing spiral density waves, all of them made of countless particles of ice and rock, ranging in size from dust grains to boulders, orbiting Saturn in a flat plane that stretches hundreds of thousands kilometers, but is, in most places, only tens of meters thick. The Voyagers discovered new moons and revealed the diversity of Saturn's moon system. Titan, the largest of Saturn's moons and the second largest in the solar system, showed a thick, hazy atmosphere that completely obscured its surface, an atmosphere made mostly of nitrogen, like Earth's, but much colder, with methane playing the role that water plays in Earth's atmosphere, forming clouds, raining down to the surface, and pooling in lakes. Enceladus, a small moon that should by all rights be a frozen, dead world, revealed something astonishing: active geysers erupting from cracks near its south pole, spraying water ice and organic molecules into space, evidence of liquid water beneath its icy surface and the possibility, however remote, of conditions that could support life. Voyager 2 continued on to Uranus and Neptune, planets so distant that even travelling at tens of thousands of kilometers per hour, it took years to reach them. Uranus, tipped on its side so that its poles point toward the Sun during parts of its orbit, showed a bland, featureless atmosphere and a system of thin, dark rings. Neptune, the last stop on the Grand Tour, turned out to be far more active than Uranus despite being farther from the Sun and receiving less energy. Its atmosphere showed bands and storms, including the Great Dark Spot, a storm system similar to Jupiter's Great Red Spot but smaller, and as later observations revealed, temporary. Neptune's largest moon, Triton, turned out to be one of the coldest objects in the solar system but also geologically active, with geysers of nitrogen erupting from its surface, driven by the feeble warmth of the distant sun, heating nitrogen ice just enough to make it sublimate and burst through weak points in the crust. After passing Neptune, both Voyager spacecraft continued outward, leaving the realm of the planets behind and heading toward interstellar space. They are still traveling, still sending back data when they have power and a story to tell, now more than 15 billion kilometers from Earth, moving through a region where the sun's influence fades and the environment of the galaxy begins. They carry with them golden records, literally gold-plated copper discs containing sounds and images selected to portray the diversity of life and culture on Earth, a message in a bottle flung into the cosmic ocean with no expectation that it will ever be found, but created anyway as an expression of hope and greeting to whatever might be out there. Following the Voyagers, other missions have continued to explore the outer solar system. The Galileo spacecraft orbited Jupiter for 8 years, studying the planet and its moons in detail, confirming the existence of Europa's subsurface ocean, and discovering that Ganymede has its own magnetic field, something no other moon in the solar system possesses. The Cassini mission spent 13 years orbiting Saturn, revolutionizing our understanding of the planet, its rings, and its moons. It deployed a probe called Huygens that descended through Titan's atmosphere and landed on its surface, sending back the first images from the surface of a moon in the outer solar system, showing a landscape of rounded ice boulders sitting on a dark plain with a hazy orange sky above. Cassini repeatedly flew past Enceladus, flying through its geysers and analyzing their composition, finding not just water but also organic molecules, the building blocks of life as we know it. These discoveries transformed these distant moons from curiosities into potential destinations for future missions searching for life beyond Earth. The outer solar system is a place of extremes. The temperatures are so cold that the atmosphere of Titan allows methane to exist as a liquid, forming rivers and lakes. On Triton, nitrogen ice sublimates directly from solid to gas. On Europa and Enceladus, ice forms a shell dozens of kilometers thick above oceans that may be tens or hundreds of kilometers deep. The distances are so vast that light from the Sun, which reaches Earth in just over 8 minutes, takes more than 4 hours to reach Neptune. A radio signal sent from a spacecraft in the outer solar system takes hours to reach Earth, and by the time controllers receive the signal and send a response, the situation that prompted the signal has long since passed. This means that spacecraft exploring the outer solar system must be largely autonomous, capable of making decisions and responding to problems on their own, with only general guidance from Earth. And yet, despite the distance and the cold and the darkness, these worlds are not dead. They are active, changing, full of processes we are only beginning to understand. The ice volcanoes of Enceladus, the methane rain of Titan, the sulfur geysers of Io, the magnetic fields of Jupiter and Ganymede, the thin atmospheres of some moons and the thick atmosphere of Titan, all of these phenomena challenge our understanding of how worlds work and expand the range of environments where interesting chemistry and perhaps even life might exist. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies left over from the formation of the solar system, chunks of rock and ice that never coalesced into planets. Pluto, once considered the 9th planet but now classified as a dwarf planet, is the most famous resident of this region, but it is only one of many. In 2015, the New Horizons spacecraft flew past Pluto and revealed a world far more complex than anyone expected. Instead of a cratered, dead ice ball, New Horizons found a world with vast plains of nitrogen ice, mountains of water ice as hard as rock rising several kilometers high, and signs of recent geological activity, features that could be only millions of years old on a world that formed more than 4 billion years ago. The images showed a heart-shaped region of smooth ice, informally named Tombor Regio, after Pluto's discoverer, that appears to be constantly repaved by convective processes, the ice slowly flowing and churning in response to heat from Pluto's interior, heat from the decay of radioactive elements trapped inside when the world formed. Pluto's largest moon, Charon, is so large relative to Pluto that the two worlds orbit a common center of gravity located in space between them, making them essentially a double planet. Charon's surface shows canyons and cliffs that suggest its interior froze and expanded at some point, cracking the surface. New Horizons continued beyond Pluto to visit Arrokoth, a small, reddish object that turned out to be two lobes stuck together. A snowman-shaped world that represents one of the most primitive objects ever visited by a spacecraft, a leftover from the very formation of the solar system, unchanged for billions of years, a messenger from the earliest days of our cosmic neighborhood. The outer solar system is a reminder that our solar system is far larger and more complex than the small region around the Sun where Earth resides. It is a place where worlds are made of ice instead of rock, where moons are more interesting than planets, where distances are so vast that entire years pass between opportunities to visit, and where the Sun is just a bright star in a black sky, providing little warmth and less comfort. And yet it is our solar system, part of the same family of worlds that includes Earth, shaped by the same events that shaped our planet, built from the same cloud of gas and dust that collapsed to form the Sun billions of years ago. As you rest now, let your mind wander outward past the orbit of Mars, through the asteroid belt, belt, past Jupiter's churning storms and Saturn's gleaming rings, past the tilted world of Uranus and the blue depths of Neptune, out to the icy realm where Pluto circles in the cold and dark, and farther still to the edge where the sun's influence fades and the true emptiness of interstellar space begins. These worlds exist right now, even as you lie here, even as you drift towards sleep. They are out there, circling the sun, unchanged by your awareness or lack of it, real places with mountains and valleys and storms and silence. And we have seen them. We have sent our machines to visit them, to photograph them, to measure them, to report back what they found. The outer solar system is no longer unknown. It is simply far away. And in that distance, in that cold darkness, in those strange worlds, so unlike our own, we find not answers, but better questions. Questions about how worlds form and change, about where life might arise, about what else might be possible in this vast and varied universe. Among all the worlds that NASA has explored, few have captured the imagination quite like the moons that hide oceans beneath shells of ice. These are not oceans you can see from space. Their surfaces are frozen solid, covered in ice that can be tens of kilometers thick, ice that never melts because these moons orbit far from the sun, where sunlight is weak and temperatures plunge to extremes that would freeze any familiar substance solid. But beneath that ice, warmed by forces that have nothing to do with the sun, liquid water exists, vast oceans that contain more water than all of Earth's oceans combined, oceans that have existed for billions of years, isolated from the surface, hidden in darkness, and possibly, just possibly, harbouring life. The most famous of these hidden ocean worlds is Europa, one of Jupiter's 4 large moons, discovered by Galileo in 1610 when he turned his primitive telescope toward Jupiter and saw 4 points of light moving around the planet, proof that not everything in the heavens orbited Earth. For centuries, Europa was just one of those points of light, a name in a list, a destination for mathematical calculations of orbital mechanics, but not a place anyone could truly know. That changed when the Voyager spacecraft flew past in 1979 and returned images showing Europa's surface in detail for the first time. What they revealed was astonishing. Europa's surface is unlike anything else in the solar system, a ball of ice almost entirely devoid of craters, which means the surface must be young, constantly renewed by some process that erases the impact scars that accumulate on every other solid surface in the solar system. The ice is crisscrossed with dark lines, thousands of them, some straight, some curved, some branching and intersecting in complex patterns that scientists call chaos terrain. These lines are cracks in the ice, fractures where the surface is broken and shifted, sometimes pulling apart to create ridges, sometimes sliding past each other like faults on Earth. Some areas show blocks of ice that appear to have broken apart and then frozen in place again, like a jigsaw puzzle that has been taken apart and reassembled slightly wrong, the pieces no longer quite fitting together. All of this evidence pointed to a conclusion that seemed almost too extraordinary to believe. Beneath the ice, there must be an ocean, and that ocean must still be liquid, warmed from below, allowing the ice shell to flex and crack and shift in response to the tides raised by Jupiter's enormous gravity. When the Galileo spacecraft arrived at Jupiter in 1995 and spent years studying the system, it confirmed what Voyager had hinted at. Galileo's instruments measured Europa's magnetic field and found that it changes in a way that can only be explained by the presence of a conducting layer beneath the surface, and salt water is an excellent conductor. Galileo's cameras photographed the surface in much higher resolution, revealing details of the cracks and chaos regions, showing areas where it looks like warm ice from below has pushed up through the cold surface, carrying with it whatever materials were dissolved in the water below, materials that leave reddish and brownish stains on the otherwise white ice, stains whose exact composition is still debated, but which include salts and possibly organic molecules. The ocean beneath Europa's ice is kept liquid by tidal heating, the same process that drives the volcanoes on Io, but operating at a gentler level. As Europa orbits Jupiter, the giant planet's gravity pulls on the moon, stretching and squeezing it in a cycle that repeats with each orbit. This constant flexing generates heat through friction. The same way bending a metal wire back and forth makes it warm, the heat is not enough to melt the surface, which remains frozen at temperatures around -160 degrees Celsius, but deeper down, it is enough to keep water liquid, possibly for billions of years. Scientists estimate that Europa's ocean could be 100 kilometers deep, far deeper than any ocean on Earth, with a volume of water 2 or 3 times that of all Earth's oceans combined, and unlike Earth's oceans, which are exposed to the atmosphere and sunlight, Europa's ocean exists in complete darkness, sealed beneath an ice shell that could be 20 or 30 kilometers thick at the equator, possibly thinner near the poles, insulated from space, stable and undisturbed. This stability is both fascinating and challenging. On Earth, life as we know it depends on energy from the sun, captured by plants and other photosynthetic organisms that form the base of almost every food chain, but Europa's ocean has no sunlight. If life exists there, it would have to depend on other sources of energy, likely chemical energy from reactions between water and rock at the ocean floor, similar to the ecosystems discovered in Earth's deep oceans near hydrothermal vents, places where superheated water emerges from cracks in the ocean floor, carrying dissolved minerals that support communities of bacteria, tube worms, clams, and other creatures that live in complete darkness, independent of the sun. If Europa has similar vents, if its rocky core is in contact with its ocean, and if water circulates through cracks in that rock, picking up minerals and heat, then the basic conditions for life, as we understand it, might exist there. Liquid water, chemical energy, and the organic molecules that form the building blocks of life. Of course, the presence of these conditions does not mean life exists. It only means life is possible, and the gulf between possible and actual is vast. Europa is not the only moon with a hidden ocean. Enceladus, a small moon of Saturn only about 500 kilometers across, revealed its secret in spectacular fashion when the Cassini spacecraft observed plumes of water vapor and ice particles erupting from cracks near its south pole, geysers shooting material hundreds of kilometers into space. Some of the material falls back to the surface, giving Enceladus one of the most reflective surfaces in the solar system, constantly covered in fresh, clean ice. But much of the material escapes, forming a faint ring around Saturn made of particles from Enceladus, and some of it streams out into space along Saturn's magnetic field lines. Cassini flew through these plumes multiple times, analysing their composition with its instruments, and discovered that they contain not just water, but also salt, meaning the water came from a salty ocean, and organic molecules, including some that are relatively complex. The discovery that Enceladus has an ocean was unexpected, because the moon is so small it should have frozen solid billions of years ago. But tidal heating from Saturn, combined with an orbital resonance with another moon that keeps Enceladus's orbit slightly elliptical, generates enough heat to maintain liquid water beneath the ice, concentrated in a global ocean or possibly a regional sea near the South Pole. The geysers provide a way to sample the ocean without needing to drill through kilometers of ice, making Enceladus one of the most promising targets in the search for life beyond Earth. Ganymede, the largest moon in the solar system, also appears to have a subsurface ocean, and possibly more than one, layers of liquid water sandwiched between layers of ice of different densities and structures, an arrangement possible only on a world where the pressures and temperatures create exotic forms of ice that are denser than liquid water and sink rather than float. Callisto, another of Jupiter's moons, may have an ocean as well, though evidence is less certain, and Titan, Saturn's largest moon, is thought to have a subsurface ocean of liquid water beneath its icy crust, in addition to the lakes and seas of liquid methane and ethane that exist on its surface. Each of these worlds represents a different variation on the theme of hidden oceans, each one shaped by slightly different conditions of temperature, pressure, tidal forces, and orbital dynamics. Together, they suggest that liquid water, long thought to be rare in the universe, may actually be quite common, at least in the outer regions of planetary systems where icy moons are abundant. The implications of this realization are profound. For most of human history, when we thought about life beyond Earth, we imagined it on planets, worlds orbiting stars at the right distance to have liquid water on their surfaces, the so-called habitable zone. But the hidden ocean worlds of the outer solar system do not need to be in a habitable zone. They create their own heat through tidal forces, independent of their distance from the sun. This means that even in a solar system with no planets in the habitable zone, life might still be possible on moons orbiting giant planets. It vastly expands the number of potentially habitable environments in the universe. NASA is planning missions to explore these ocean worlds in greater detail. The Europa Clipper spacecraft, scheduled to launch in the 2020s, will orbit Jupiter and make dozens of close flybys of Europa, mapping the surface, measuring the thickness of the ice, analysing the composition of surface materials, and searching for places where the ocean might be closer to the surface, or where water might occasionally erupt through cracks, as it does on Enceladus. Future missions might include landers that could sample surface ice and analyse it for organic molecules and biosignatures, or even submarines that could melt through the ice and explore the ocean directly, though such missions are decades away and present enormous technical challenges. For now, we are left with observations from a distance, images of cracked ice and mysterious plumes, measurements of magnetic fields and gravitational anomalies, all of them painting a picture of worlds that are far more dynamic and potentially hospitable than anyone imagined a few decades ago. As you rest here, consider the strangeness of it. Oceans larger than Earth's oceans, existing in perpetual darkness, sealed beneath ice so thick that no light from above could ever penetrate, kept liquid by the tidal pull of giant planets, possibly teeming with microbial life, possibly utterly sterile, we do not know. They are there right now, even as you close your eyes, even as your breathing slows and deepens. On Europa, cracks in the ice might be widening, releasing a brief plume of water vapour that freezes instantly in the vacuum and falls back as snow. On Enceladus, geysers are erupting, shooting water and organics into space, where some of it catches the sunlight and sparkles like diamonds before falling back or escaping forever. On Titan, methane rain might be falling onto hydrocarbon seas, while far below, a water ocean sits sealed away, perhaps completely isolated from the strange chemistry of the surface, perhaps connected through cracks and channels we have not yet discovered. These worlds exist at the edge of what we have explored, tantalizingly close in cosmic terms, but still requiring years of travel to reach. They represent some of the most promising destinations in the search for life beyond Earth, not because we have found life there, but because we have found the conditions that might allow life to exist: water, energy, chemistry, stability, time. Whether life has taken advantage of those conditions is a question we cannot yet answer, but the fact that we can ask the question, that we can identify specific places where the search might be fruitful, that we can plan missions to go and look, represents a remarkable shift in human understanding. A century ago, the idea of oceans on moons of Jupiter and Saturn would have been pure fantasy. 50 years ago, it was speculation. Today it is confirmed reality. And in the coming decades, we may finally learn whether those hidden oceans are as empty as they seem, or whether they harbour the second genesis of life, a completely independent origin of biology that would prove, once and for all, that life is not unique to Earth, that it arises wherever conditions allow, that the universe is not just vast and ancient, but also, possibly, abundantly alive. Look up on a clear night far from city lights, and you can see the Milky Way stretching across the sky, a pale band of light that ancient cultures interpreted as a river, a road, or the backbone of the night. It is, of course, our galaxy seen from the inside, the combined light of billions of stars, too distant and faint to see individually but together, creating a faint glow. But scattered along that band, visible even to the naked eye in the darkest skies, are brighter patches, fuzzy regions that do not look quite like stars. These are nebulae, vast clouds of gas and dust floating in space, and they are among the most beautiful and scientifically important objects that NASA's telescopes have revealed. The word nebula comes from the Latin word for cloud, and that is essentially what they are. Clouds made not of water vapour, but of hydrogen, helium, and trace amounts of heavier elements, mixed with tiny grains of dust, particles smaller than the width of a human hair, made of carbon, silicon, and other elements forged in the cores of earlier generations of stars and released into space when those stars died. These clouds are vast beyond comprehension. often stretching for tens or hundreds of light years, regions so large that light itself, traveling at 300,000 kilometers per second, takes decades or centuries to cross from one side to the other. And yet, for all their size, they are extraordinarily diffuse. If you could scoop up a cubic meter of material from a typical nebula, it would contain fewer atoms than the best vacuum we can create in laboratories on Earth. By any ordinary standard, a nebula is emptiness, but there is so much of it, so much empty space filled with just a few atoms per cubic centimeter, that when you add it all up, there is enough material to build not just planets but stars, hundreds or thousands of stars, each one with its own potential family of worlds. Nebulae come in different types, each one representing a different stage in the cycle of stellar birth and death. Some are stellar nurseries, places where new stars are being born from the gravitational collapse of gas and dust. Others are the beautiful death shrouds of stars that have reached the end of their lives, throwing off their outer layers in a final display before fading away. And some are the remnants of violent stellar explosions, expanding shells of gas driven outward by the unimaginable energies released when massive stars die. Each type tells a part of the story of how matter moves through the universe, how it is gathered together to make stars and planets, how it is transformed inside stars through nuclear fusion, and how it is returned to space to be used again in the next generation of star formation. The Orion Nebula, visible even to the naked eye as the middle star in Orion's sword, is one of the closest and most studied star-forming regions. Located about 1,350 light-years from Earth, it is a vast cloud of gas and dust illuminated by the light of young, hot stars that have recently formed within it. Photographs taken by the Hubble Space Telescope reveal extraordinary detail. Glowing clouds of hydrogen and oxygen in shades of red and green, dark pillars of dense dust where the light cannot penetrate, and scattered throughout the nebula, thousands of young stars, some still surrounded by disks of material from which planets may be forming. The Orion Nebula is a reminder that star formation is not a rare event, but an ongoing process. Right now, even as you rest here, stars are being born in that cloud and in thousands of other nebulae across our galaxy and billions of galaxies beyond. The process begins when a region of a nebula becomes slightly denser than its surroundings, perhaps because of a passing shock wave from a nearby supernova, or simply through random fluctuations. Gravity takes over, pulling more material into the dense region, causing it to contract. As it contracts, it heats up, and as it heats up, it begins to glow, first in infrared, which can pass through the dust that hides the process from visible light, and eventually invisible light as well. Over hundreds of thousands of years, the core of the collapsing cloud becomes hot enough and dense enough for nuclear fusion to begin, the process by which hydrogen atoms are forced together under immense pressure and temperature to form helium, releasing energy in the process. At that moment, a new star is born, and the light and wind from that star begin to blow away the remaining gas and dust around it, revealing the newborn star to the universe. But star formation is not solitary. Stars tend to form in clusters, sometimes dozens, sometimes thousands at a time, all born from the same cloud, all roughly the same age. The Pleiades, a cluster of bright stars visible in the constellation Taurus, is a young cluster, only about 100 million years old, still loosely bound together by gravity. Hubble's images of star-forming regions show not just one or two young stars, but entire populations at different stages of formation, some still deeply embedded in their cocoons of gas and dust, others already emerging, their light beginning to illuminate the surrounding cloud, creating the glowing nebulae we see. One of the most famous images from Hubble is the so-called Pillars of Creation, a photograph of a region within the Eagle Nebula showing 3 towering columns of dense gas and dust, each several light-years tall, backlit by the glow of young stars. The pillars are being slowly eroded by the intense radiation from those stars, their surfaces boiling away into space. But within the pillars, protected from the radiation, new stars are forming. The image is both creation and destruction, showing how the birth of stars is a violent, dynamic process shaped by the light and wind from the stars themselves, a process that feeds back on itself, with one generation of stars influencing the formation of the next. But not all nebulae are places of birth. Some are places of death. or more accurately, places of transformation. Planetary nebulae, despite their name, have nothing to do with planets. The name comes from early astronomers who, looking through small telescopes, thought these objects looked like the round disks of planets. In reality, they are shells of gas thrown off by stars similar to the Sun when they reach the end of their lives. When a star like the Sun exhausts the hydrogen fuel in its core, it begins to burn helium, then heavier elements, and eventually it becomes unstable, pulsating and throwing off its outer layers in a gentle wind that gradually expands into space. What remains at the center is the hot core of the star, now exposed, radiating ultraviolet light that causes the expanding shell of gas to glow in beautiful, complex patterns. The Ring Nebula, the Helix Nebula, the Cat's Eye Nebula, these are all planetary nebulae, each one unique, each one showing a different pattern of symmetry and structure that scientists are still working to understand. Some are perfect spheres, others are elongated or bipolar, and some show intricate filaments and knots that suggest complex interactions between the expanding gas and magnetic fields or companion stars. They are all, in essence, obituaries written in light, the final messages of stars announcing their transformation from active fusion-powered engines into white dwarfs, dense embers that will cool slowly over trillions of years. But the most spectacular nebulae are the remnants of supernovae, the explosions of massive stars that have reached the end of their lives and gone out not with a whimper, but with a bang that briefly outshines an entire galaxy. When a star much more massive than the Sun exhausts its fuel, it can no longer support itself against its own gravity. The core collapses in a fraction of a second, and the outer layers rebound in an explosion that releases more energy in a few seconds than the Sun will emit in its entire 10 billion year lifetime. The explosion throws the star's outer layers into space at speeds of thousands of kilometers per second, creating a shockwave that plows into the surrounding interstellar medium, heating it, compressing it, and causing it to glow. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054 CE, is still expanding and glowing today, nearly 1,000 years later. At its center is a pulsar, a rapidly spinning neutron star, the collapsed core of the original star, now compressed to a sphere only about 20 kilometers across, but containing more mass than the Sun. The pulsar spins about 30 times per second, and its rotation sends beams of radiation sweeping across space like a cosmic lighthouse, energizing the surrounding nebula and creating the complex filamentary structure visible in Hubble images. Supernova remnants are important for more than their beauty. They are the primary way that heavy elements heavier than helium, are distributed through the galaxy. The hydrogen and helium that make up most of the universe were created in the Big Bang, but all the heavier elements, carbon, nitrogen, oxygen, iron, gold, uranium, all of them were created inside stars through nuclear fusion and then scattered into space by supernovae. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood was created inside a star and released into space when that star died. We are, quite literally, made of stardust, and nebulae are the mechanism by which that stardust is recycled, gathered into new clouds, collapsed into new stars, and incorporated into new planets, and sometimes into living things that can look back at the nebulae and understand where they came from. NASA's telescopes have revealed nebulae in exquisite detail across the electromagnetic spectrum. Hubble's visible light images show the glowing gas in vivid colors, red from hydrogen, green from oxygen, blue from other elements. The Spitzer Space Telescope, which observed in infrared, could see through the dust to reveal the stars forming within, showing heat that visible light cannot detect. The Chandra X-ray Observatory reveals the hottest regions, places where shockwaves and high-energy processes create X-rays. And the James Webb Space Telescope, the most powerful telescope ever launched, combines infrared sensitivity with unprecedented resolution, revealing details of star formation and the composition of nebulae that were previously invisible. One of Webb's first images, released in 2022, showed the Carina Nebula, a massive star-forming region about 7,600 light-years away, in such detail that individual forming stars, still surrounded by their dusty cocoons, could be seen. the image looked like a landscape, a cliff or mountain range of gas and dust with stars scattered above like lights in a night sky. But the cliff is actually a wall of gas and dust being eroded by intense radiation from young stars just beyond the edge of the image, and the scale is staggering. The cliff is several light years tall, and each of those points of light is a star, possibly with planets, possibly someday, with civilizations of its own wondering about their place in the universe. As you rest here, let your mind drift among these clouds of glowing gas. Imagine yourself floating in the darkness near the Orion Nebula, watching young stars ignite one by one like lights turning on in a vast city. Feel the warmth of their light on your face, even though they are so far away. Listen to the silence that would surround you, a silence so complete that no sound from Earth or anywhere else could reach you, only the faint whisper of particles from the solar wind and the steady background hum of radiation left over from the Big Bang. Imagine drifting through a planetary nebula, the delicate shells of gas glowing in soft pastels, expanding slowly outward, and at the center, the dying star, small and white and hot, a monument to billions of years of fusion now winding down into eternal quiet. Imagine standing at the edge of a supernova remnant, watching the shockwave expand, glowing filaments twisting and turning in the magnetic fields, and knowing that everything around you, every atom of gas, every grain of dust, was once inside a star, forged in the nuclear fires of its core, and is now returning to the interstellar medium to be used again. These nebulae are real. They exist right now, light years away, glowing in the darkness, shaping the evolution of the galaxy, creating the elements necessary for life, and inspiring wonder in everyone who sees their images. They are part of the cosmic cycle, the endless process by which matter is gathered, transformed, and dispersed again, a process that has been happening for billions of years and will continue for billions more. And in that process, in that cycle of birth and death and rebirth, we find not just the history of stars, but the history of everything, including ourselves. If you could step outside the Milky Way and look back at it from a distance, you would see not a band of light but a vast spiral, a disk of stars rotating slowly around a bright central bulge, spiral arms curling outward from the center, glowing regions where new stars are forming, darker lanes where dust blocks the light, and surrounding it all, a faint halo of old stars and globular clusters, spherical collections of hundreds of thousands of stars that orbit the galactic center like distant moons. Our galaxy contains between 200 and 400 billion stars, though the exact number is uncertain, and it stretches about 100,000 light-years from edge to edge. The Sun is located about halfway out from the center, in a relatively quiet region between two spiral arms, and it takes the Sun about 225 million years to complete one orbit around the galactic center, which means that since the Sun formed about 4.6 billion years ago, it has completed only about 20 orbits. Dinosaurs lived on Earth during the last time the Sun was on the opposite side of the galaxy from where it is now. That is the scale of galactic time, slow and measured in units that make human history seem like a brief flicker. But the Milky Way, vast as it is only one galaxy among billions in the observable universe, and understanding that took humanity a surprisingly long time. For most of history, astronomers were not certain whether the fuzzy nebulae they observed through telescopes were clouds within our galaxy, or separate galaxies in their own right. The debate was settled in the 1920s when Edwin Hubble, using the largest telescope available at the time, measured the distance to the Andromeda Nebula and proved that it was far beyond the boundaries of the Milky Way, a separate galaxy containing billions of stars, similar in size and structure to our own. The realization that the universe contains countless galaxies, each one a vast collection of stars, was one of the most profound shifts in human understanding, comparable to the realization that Earth is not the center of the solar system, or that the Sun is just one star among many. NASA's telescopes have allowed us to see galaxies in unprecedented detail and at unprecedented distances, distances so great that the light we see left those galaxies billions of years ago, when the universe was much younger. The Hubble Space Telescope's deep field images, created by pointing the telescope at a seemingly empty patch of sky and collecting light for days, revealed thousands of galaxies in that one small region, galaxies of every shape and size, some spiral like the Milky Way, some elliptical, some irregular, and some so distant and faint that they appear only as tiny smudges of light. Each of those galaxies contains billions or even hundreds of billions of stars, and each star is a sun, potentially with its own system of planets. The numbers become almost meaningless at this scale, but they point to a universe far richer and more complex than our ancestors could have imagined. Galaxies are not evenly distributed through space. They cluster together, drawn by gravity into groups and clusters and superclusters, forming a vast cosmic web with filaments of galaxies stretching across hundreds of millions of light years, separated by vast voids where few galaxies exist. The Milky Way is part of a small group called the Local Group, which includes Andromeda, the largest member, the Milky Way, and about 50 smaller galaxies. The Local Group, in turn, is part of the Virgo supercluster, a larger structure containing thousands of galaxies spread across about 110 million light-years. And the Virgo supercluster is itself just one small part of an even larger structure called Laniakea, a supercluster of superclusters containing about 100,000 galaxies. Mapping these structures and understanding how they formed is one of the major goals of modern cosmology, the study of the universe as a whole. Galaxies come in different types, and understanding why they have different shapes and structures is an ongoing area of research. Spiral galaxies like the Milky Way have rotating disks with spiral arms, regions where gas is compressed and new stars are forming. Elliptical galaxies are more rounded, with older stars and little ongoing star formation. Irregular galaxies have no clear structure, often because they have been disturbed by gravitational interactions with other galaxies. And then there are active galaxies with supermassive black holes at their centers that are actively feeding on gas and stars, producing enormous amounts of energy in the process, sometimes more energy than all the stars in the galaxy combined. These active galactic nuclei, as they are called, can emit jets of material travelling at nearly the speed of light, jets that stretch for hundreds of thousands of light years, visible in radio waves and X-rays, powered by matter falling into black holes millions or billions of times more massive than the Sun. One of the most remarkable discoveries made possible by NASA telescopes is how galaxies change over time. By observing distant galaxies, we are looking back in time, seeing them as they were billions of years ago, because of the time it takes light to travel across the universe. What these observations reveal is that galaxies in the early universe were smaller, more irregular, and more actively forming stars than galaxies today. Over billions of years, galaxies grew through mergers, colliding and combining with other galaxies, and through the steady accretion of gas from the intergalactic medium, our own Milky Way has consumed numerous smaller galaxies over its history, and it is currently in the process of absorbing a few more small dwarf galaxies that are being pulled apart by the Milky Way's gravity, their stars scattered into streams that wrap around our galaxy. In a few billion years, the Milky Way and Andromeda will collide, a slow-motion merger that will take hundreds of millions of years to complete, eventually forming a single, larger elliptical galaxy that astronomers have playfully nicknamed Milkomeda. The collision will not destroy stars, because the distances between stars are so vast that direct collisions are extremely unlikely, but it will disrupt the structure of both galaxies, trigger bursts of new star formation as gas clouds collide and compress, and eventually settle into a new equilibrium. Observing distant galaxies also allows astronomers to study the history of the universe itself. The most distant galaxies observed by the James Webb Space Telescope are seen as they were only a few 100 million years after the Big Bang, at a time when the universe was less than 1 billion years old, a small fraction of its current age of about 13.8 billion years. These early galaxies are smaller and less developed than modern galaxies, but they are remarkably bright and actively forming stars, condensing out of the primordial gas left over from the Big Bang. By studying these galaxies, astronomers can test models of how the first structures formed, how stars and black holes came into existence, and how the chemical elements heavier than hydrogen and helium gradually accumulated through successive generations of star formation. One of the surprises from Webb's observations is that some of these early galaxies appear more massive and well-formed than models predicted, suggesting that galaxy formation began earlier and proceeded faster than expected, a reminder that the universe still has secrets to reveal and that our understanding, though vastly improved, is far from complete. Light from these distant galaxies has been travelling through space for billions of years, and during that time, the universe itself has been expanding, stretching the space between galaxies and lengthening the wavelength of the light, shifting it from visible light toward the infrared in a process called redshift. The amount of redshift tells astronomers how far away a galaxy is and how long its light has been travelling, making redshift a kind of cosmic clock, a way to measure not just distance but time. Looking deeper into space means looking farther back in time, and the most distant objects we can see are the most ancient, their light offering a glimpse of the universe as it was in its infancy. The expansion of the universe, discovered by Edwin Hubble in the 1920s, is one of the most important findings in all of science. Evidence that the universe is not static and eternal but dynamic and evolving, that it had a beginning, the Big Bang, and that it has been changing ever since. NASA missions have played a crucial role in measuring the expansion rate, known as the Hubble constant, though recent measurements have revealed a puzzling inconsistency. Different methods of measuring the expansion give slightly different results, and astronomers are still working to understand why. This discrepancy, sometimes called the Hubble tension, hints that there may be something missing in our understanding of the universe, some unknown component or process that we have not yet accounted for. It is a reminder that even as we learn more, even as we map the cosmos in ever greater detail, the universe continues to surprise us, to challenge our models, to offer new mysteries to replace the ones we solve. As you lie here, drifting gently towards sleep, consider the strangeness of what we have learned. The universe is not a single unchanging thing, but a vast, evolving system, born in a hot, dense state nearly 14 billion years ago and expanding ever since, cooling as it expands, allowing matter to clump together under gravity to form the first stars, the first galaxies, and eventually the complex structures we see today. Every galaxy, every star, every planet, every atom in your body is part of that story, forged in the nuclear fires of stars, scattered by supernovae, gathered into new clouds, collapsed into new stars, and eventually, in at least one case we know of, organized into living things capable of looking back across billions of light years and understanding, at least in part, where they came from. The light from distant galaxies takes so long to reach us that by the time we see it, the galaxies have moved, the universe has expanded, and what we see is not where they are now, but where they were billions of years ago. We are looking at ghosts, ancient light from ancient places, some of which may no longer exist in the form we see, and yet that light carries information encoded in its wavelength and intensity, information about the composition of those galaxies, their motion, their age, their distance, all of it readable if we have the instruments and the knowledge to decode it, and we do. NASA's telescopes, Hubble, Spitzer, Chandra, and now Webb, have given us the tools to read that ancient light, to piece together the history of the universe from the faint signals that reach us across the void, to build a picture of the cosmos that is richer, stranger, and more beautiful than anyone imagined. The galaxies are out there right now, even as you close your eyes. Billions of them, each one a vast city of stars, some nearby, some unimaginably distant, some young and bright, some old and fading, all of them moving through space, all of them part of the great cosmic dance that has been unfolding since the beginning of time. And in observing them, in studying their light, in mapping their positions and measuring their motions, we are not separate observers but participants, part of the same universe, made of the same atoms, subject to the same laws, connected by threads of gravity and light to everything else that exists. There are places in the universe where the rules seem to break down, where the familiar laws of physics are pushed to their limits and beyond, where space itself is bent and twisted into shapes that defy easy understanding, and where time flows differently than it does anywhere else. These places are black holes, regions where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. Black holes are not holes in the sense of empty spaces. They are the opposite, regions where matter is compressed to such extreme density that it warps the fabric of space-time itself, creating a well so deep that anything falling in is lost to the outside universe forever. The concept of a black hole was first suggested by theoretical physics long before there was any observational evidence for their existence. In the early 20th century, when Einstein published his theory of general relativity, describing gravity not as a force but as the curvature of space-time caused by mass, physicists quickly realized that the equations predicted the possibility of objects so dense that their gravity would trap even light. For decades, these solutions were regarded as mathematical curiosities, interesting but probably not real. But as astronomers studied the universe in greater detail, they began to find evidence that black holes not only existed, but were surprisingly common. The first strong evidence came from observations of binary star systems where one member was visible and the other was not, yet the visible star was clearly orbiting something massive. By measuring the orbit, astronomers could calculate the mass of the invisible companion, and in several cases, that mass was too large to be a neutron star, the densest known object other than a black hole, which meant it had to be something else, something that did not emit light, something with the properties predicted for a black hole. Further evidence came from the centers of galaxies, where stars and gas were observed orbiting at high speeds around compact, invisible points, implying the presence of enormously massive objects, millions or even billions of times the mass of the Sun, concentrated in regions smaller than our solar system. These supermassive black holes are now believed to exist at the centers of most, if not all, large galaxies, including our own Milky Way, where a black hole with a mass of about 4 million suns, called Sagittarius A star, lurks at the galactic core. NASA's telescopes and observatories have played a central role in studying black holes, detecting their presence and effects even though the black holes themselves cannot be directly seen. The Chandra X-ray Observatory has observed the intense X-ray emission produced by gas as it spirals into black holes, heated to millions of degrees by friction and compression until it glows brightly in X-rays just before crossing the event horizon and vanishing forever. These observations reveal not just the existence of black holes, but details about their size, spin, and how they interact with their surroundings. When gas falls into a black hole, it does not plunge straight in, but forms a swirling disk called an accretion disk, where the gas orbits the black hole at speeds approaching the speed of light, gradually spiraling inward as friction and magnetic fields drain away its angular momentum. As the gas heats up, it radiates energy, and in some cases, the black hole can convert a significant fraction of the infalling matter's mass into energy through this process, making actively feeding black holes some of the most luminous objects in the universe. Quasars, the brightest objects known, are powered by supermassive black holes in the centers of distant galaxies, feeding on vast amounts of gas and shining with the light of trillions of suns, visible across billions of light years. Some black holes also produce jets, narrow beams of material and energy ejected at nearly the speed of light from regions near the event horizon, driven by magnetic fields twisted and amplified by the rotating black hole. These jets can extend for hundreds of thousands of light years, far beyond the galaxy that hosts the black hole, and their exact mechanism is still not fully understood, though they are among the most energetic and dramatic phenomena in the universe. One of the most remarkable achievements in the study of black holes came in 2019 when the Event Horizon Telescope, a global network of radio observatories working together to create a single, Earth-sized virtual telescope, captured the first direct image of a black hole's event horizon. The target was the supermassive black hole at the center of the galaxy M87, located about 55 million light-years from Earth. The image showed a bright ring of light surrounding a dark central region, exactly as predicted by general relativity. The bright ring is the glow of the accretion disk, and the dark region is the shadow of the event horizon, the boundary beyond which nothing can escape. The shadow is larger than the event horizon itself because the intense gravity bends light around the black hole, creating a region where light can orbit the black hole temporarily before either escaping or falling in. The image was a triumph of both technology and theoretical physics, confirming predictions made decades earlier and providing direct visual evidence of one of the strangest predictions of Einstein's theory. In 2022, the Event Horizon Telescope released a second image, this time of Sagittarius A star, the supermassive black hole at the center of our own galaxy. Though closer than M87's black hole, Sagittarius A star is much smaller and more difficult to image because the material around it changes on timescales of minutes, requiring sophisticated techniques to combine data collected over many hours. The image again showed a bright ring surrounding a dark shadow, consistent with a spinning black hole about 4 million times the mass of the Sun. Black holes come in different sizes. Stellar mass black holes, formed from the collapse of massive stars at the end of their lives, typically have masses between about 3 and a few dozen times the mass of the Sun. Supermassive black holes, found at the centers of galaxies, have masses ranging from millions to billions of solar masses, and recent observations have hinted at the existence of intermediate mass black holes, with masses between these two ranges, though these remain more difficult to detect and study. There is also a theoretical possibility of much smaller black holes, primordial black holes, that could have formed in the early universe, though none have been definitively observed. What happens if something falls into a black hole is one of the most fascinating and disturbing questions in physics. From the perspective of someone far away, watching an object fall toward a black hole, the object appears to slow down as it approaches the event horizon, its light becoming increasingly red-shifted and dimmer until eventually it seems to freeze at the horizon, never quite crossing it, though in reality it has long since passed the point of no return. This is because time itself is affected by gravity, and near the event horizon, time flows so much more slowly relative to distant observers that the infalling object appears to take an infinite amount of time to cross. But from the perspective of the infalling object, nothing special happens at the event horizon. It crosses the boundary in a finite amount of time and continues falling toward the singularity at the center, the point where all the mass of the black hole is concentrated, and where the curvature of space-time becomes infinite, at least according to general relativity. What really happens at the singularity is unknown because our current theories break down under such extreme conditions, and understanding this requires a theory of quantum gravity that successfully unites general relativity with quantum mechanics, a theory that physicists have been seeking for decades but have not yet found. Black holes also raise profound questions about information and the nature of reality. According to quantum mechanics, information cannot be destroyed, but black holes seem to violate this principle because anything that falls into a black hole disappears from the outside universe, taking its information with it. If the black hole eventually evaporates through a process called Hawking radiation, a slow leakage of energy predicted by quantum mechanics, the information seems to be lost forever, creating a paradox. Physicists have proposed various solutions, including the idea that information is somehow encoded on the event horizon itself, or that it is released in subtle ways in the Hawking radiation, but the question remains unresolved and is one of the most important open problems in theoretical physics. As you rest here, let yourself imagine the strangeness of these objects. Picture a region of space where gravity is so intense that if you were falling toward the event horizon feet first, the difference in gravitational pull between your feet and your head would stretch you into a long, thin strand in a process gruesomely called spaghettification. Imagine crossing the event horizon, knowing that you have passed a one-way boundary, that no matter how powerful your rockets, no matter what you do, you can never return or send a signal back to the outside universe. Imagine time itself behaving strangely, the outside universe seeming to speed up as you fall, billions of years passing in moments from your perspective, though you would not survive long enough to see it. Black holes are real. They are out there right now, scattered throughout the galaxy and the universe, some quietly drifting through space, invisible except for their gravitational effects, others feeding voraciously on gas and stars, shining brilliantly in X-rays and radio waves, announcing their presence across light years. The nearest known black hole to Earth is about 1,600 light-years away, close in galactic terms, but still far enough that there is no danger. Our sun will never become a black hole because it is not massive enough, and Earth's orbit is stable and safe. But the existence of black holes reminds us that the universe contains extremes beyond our everyday experience, places where the familiar rules are stretched to breaking, where the concepts of space and time lose their ordinary meaning, and where the boundary between physics as we understand it and the unknown grows thin. They are laboratories for testing our theories, natural experiments in extreme gravity that cannot be replicated on Earth, and they are also, in strange way, beautiful. Not visually, for they are darkness-defined, but conceptually, elegant solutions to Einstein's equations, structures of pure geometry carved out of space-time by gravity, objects that challenge us to think more deeply about the nature of reality. The universe is full of phenomena that stretch the imagination, events and objects so strange that even after they are discovered and studied, they retain an air of mystery. These are the cosmic enigmas, the things that make astronomers pause and wonder, the observations that do not fit neatly into existing theories, the signals that arrive without clear explanation, and the structures that challenge our understanding of what is possible. NASA's missions have revealed many of these phenomena, not by seeking them out specifically, but by looking carefully at the universe and remaining open to surprises. One of the strangest discoveries in recent decades is the acceleration of the universe's expansion, a finding so unexpected that it earned the Nobel Prize for the astronomers who discovered it. For most of the 20th century, cosmologists assumed that the expansion of the universe, set in motion by the Big Bang, would be gradually slowing down due to the gravitational attraction between galaxies pulling on one another. The question was whether the universe contained enough matter for gravity to eventually halt and reverse the expansion, leading to a big crunch, or whether the expansion would continue forever, with the universe growing ever more dilute and cold. But observations of distant supernovae in the late 1990s revealed something completely unexpected. The expansion is not slowing down, it is speeding up. Galaxies are moving away from us and from each other at an ever-increasing rate, as if some unknown force is pushing them apart. This force, whatever it is, has been named dark energy, and it now appears to make up about 68% of the total energy content of the universe, far more than ordinary matter, which makes up less than 5%, with the rest being dark matter, another mysterious component we will return to shortly. The nature of dark energy is one of the biggest unsolved problems in physics. It could be a property of space itself, a kind of inherent energy that exists everywhere, even in what we think of as empty vacuum. This idea is related to a concept Einstein introduced and later abandoned, the cosmological constant, a term in the equations of general relativity that represents a constant energy density filling space. If dark energy is a cosmological constant, then the accelerated expansion will continue forever, and the universe will grow increasingly cold and empty over trillions of years, with galaxies moving so far apart that eventually observers in any one galaxy will see no others. The light from distant galaxies red-shifted beyond detection as the space between us and them expands faster than light can travel through it. Alternatively, dark energy could be something more dynamic, a field that changes over time, in which case the future of the universe is more uncertain. The acceleration could increase, decrease, or even reverse depending on how the field evolves. Understanding dark energy is one of the primary goals of several NASA missions, including the Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, which will survey hundreds of millions of galaxies and measure their distances and motions with unprecedented precision, providing data that could help distinguish between different theories of dark energy. Dark matter is another profound mystery. Evidence for its existence comes from many sources. The rotation of galaxies, which spins so fast that the visible stars and gas should fly apart unless there is additional unseen mass holding them together. The motion of galaxies within clusters, where the observed velocities imply far more mass than can be accounted for by visible matter. And the bending of light from distant objects by the gravity of foreground matter, an effect called gravitational lensing, which reveals the presence of mass even where nothing visible exists. All of this evidence points to the existence of a form of matter that does not emit, absorb, or reflect light, matter that interacts with ordinary matter only through gravity, making it invisible but detectable through its gravitational effects. Dark matter appears to make up about 27% of the universe's total mass energy, far more than the ordinary matter that makes up stars, planets, and everything we can see. But despite decades of searching, no one has directly detected a dark matter particle, and its exact nature remains unknown. It could be made of WIMPs, weakly interacting massive particles that occasionally collide with ordinary matter in ways that might be detectable in sensitive experiments deep underground, shielded from cosmic rays and other sources of interference. Or it could be made of axions, much lighter particles that would fill space in enormous numbers but interact so weakly with ordinary matter that they are extraordinarily difficult to detect. Or it could be something else entirely, perhaps involving physics beyond the standard model of particle physics, the framework that describes all known particles and forces except gravity. Another cosmic mystery involves fast radio bursts, brief flashes of radio waves that last only milliseconds but release as much energy as the sun emits in several days. They were first discovered in 2007 when astronomers noticed an unusual signal in archival data, and for years their origin was completely unknown, leading to wild speculation including, briefly, the possibility that they might be signals from advanced alien civilizations. Over time, astronomers detected more fast radio bursts and began to narrow down their sources, determining that they come from distant galaxies, billions of light years away, and that they are likely produced by magnetars, neutron stars with extraordinarily strong magnetic fields. When the magnetic field of a magnetar undergoes a sudden reconfiguration, a starquake of sorts, it can release a tremendous burst of energy in the form of radio waves. This explanation accounts for many observed properties of fast radio bursts, but not all, and some bursts repeat while others do not, suggesting there may be more than one mechanism at work. The study of fast radio bursts is still in its early stages, and new discoveries continue to surprise astronomers, revealing the diversity and complexity of these enigmatic events. Gamma-ray bursts are even more energetic, brief, but incredibly intense flashes of gamma rays, the highest energy form of light that occur somewhere in the universe about once per day. For a few seconds or minutes, a gamma-ray burst can outshine the entire rest of the universe in gamma rays, releasing more energy than the Sun will emit in its entire lifetime. They come in two types: short-duration bursts, lasting less than 2 seconds, which are thought to be produced by the collision and merger of two neutron stars, or a neutron star and a black hole, and long-duration bursts, which last more than 2 seconds and are associated with the collapse of massive stars into black holes, essentially a special type of supernova called a hypernova. NASA's SWIFT satellite has detected hundreds of gamma-ray bursts and, in many cases, has rapidly reoriented its instruments to observe the bursts' afterglow in X-rays and visible light, providing data that has greatly improved our understanding of these extreme events. But many questions remain, including the exact mechanisms that produce the gamma rays and why some stellar collapses produce gamma-ray bursts while others do not. Then there are the cosmic rays, high-energy particles, mostly protons that travel through space at nearly the speed of light, carrying energies far higher than anything we can produce in particle accelerators on Earth. The origins of the most energetic cosmic rays are unknown, though they are thought to be accelerated by shockwaves from supernova or other violent events. What makes them particularly mysterious is that some cosmic rays have energies so high that they should not be able to reach us from distant sources, because interactions with the cosmic microwave background radiation should slow them down and reduce their energy over large distances, a phenomenon called the GZK cutoff. Yet ultra-high energy cosmic rays above the cutoff have been detected, implying either that they come from relatively nearby sources we have not identified, or that our understanding of particle physics at these extreme energies is incomplete. Another puzzle involves the cosmic microwave background itself, the faint glow of radiation left over from the Big Bang, visible in all directions and remarkably uniform, but with tiny fluctuations that represent the seeds of all structure in the universe, regions that were slightly denser than average and eventually collapsed under gravity to form galaxies and clusters. NASA's COBE, WMAP and Planck missions have mapped these fluctuations in exquisite detail, and the data have confirmed many predictions of the Big Bang Theory and the Standard Model of Cosmology. But there are also anomalies, unexpected features in the data that do not quite match theoretical expectations, such as the so-called cold spot, a region of the sky where the temperature of the cosmic microwave background is slightly lower than average in a way that is difficult to explain, and certain alignments of fluctuations at large scales that seem improbable if they are purely random. These anomalies may be statistical flukes, but they may also be hints of new physics, evidence of events or structures that affected the early universe in ways we do not yet understand. The universe also contains voids, enormous regions of space that are nearly empty of galaxies, separated by filaments and walls of galaxies in the cosmic web. The largest void discovered so far, the Boötes void, stretches about 330 million light-years across and contains very few galaxies, far fewer than would be expected in such a large volume. Why voids exist and why they are so empty is related to the distribution of dark matter and the processes of structure formation, but their sheer size and emptiness are striking, a reminder that the universe is not uniformly filled with matter, but has a complex frothy structure on the largest scales. As you lie here, drifting gently towards sleep, let these mysteries wash over you, not as problems to be solved, but as reminders of how much we still do not know. The universe is not a finished puzzle with a few missing pieces. It is a vast, evolving system full of surprises, phenomena that challenge our understanding and push the boundaries of what we think is possible. Dark energy pulling the universe apart, dark matter holding galaxies together yet invisible and undetectable, bursts of energy arriving from distant corners of space with no clear explanation, particles traveling at energies we cannot reproduce, anomalies in the faint glow of the early universe hinting at something beyond our current models. All of these mysteries are invitations, calls to curiosity, prompts to keep looking, keep questioning, keep exploring. And every mystery that is eventually solved reveals new layers, new questions, new depths of complexity and beauty. The universe does not give up its secrets easily, but it does give them up, one discovery at a time, each one expanding our sense of what exists and how it works. For thousands of years, the only planets we knew were the ones visible in our own night sky, the wandering stars that ancient astronomers tracked across the constellations. Mercury, Venus, Mars, Jupiter, Saturn, they were familiar presences, and though we learned much about them through telescopes and spacecraft, they remained the only known planets for most of human history. The question of whether other stars had planets was asked but remained unanswered, hovering in the realm of speculation and philosophical debate. Then, in the 1990s, astronomers developed techniques sensitive enough to detect planets orbiting distant stars, and the field of exoplanet science was born, growing from a handful of discoveries to thousands, and now tens of thousands, transforming our understanding of planetary systems and raising profound questions about the nature and abundance of worlds in the universe. The first confirmed detection of an exoplanet orbiting a sun-like star came in 1995, when Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of a planet orbiting the star 51 Pegasi, located about 50 light-years from Earth. The planet, later named Dimidium, was unlike anything in our solar system, a gas giant similar in mass to Jupiter but orbiting its star in only 4 days, far closer than Mercury orbits the Sun, a so-called hot Jupiter, a type of planet that theoretical models had not predicted but that turned out to be surprisingly common. The discovery opened the floodgates. Within a few years, dozens of exoplanets were confirmed, and within 2 decades, thousands detected using a variety of methods. The radial velocity method, used for the first discovery, measures the tiny wobble in a star's motion caused by the gravitational pull of an orbiting planet. The star and planet orbit their common center of mass, and by carefully measuring shifts in the star's spectrum, astronomers can infer the presence of a planet, its mass, and its orbital period. The transit method, which has proven even more productive, detects planets by observing the slight dimming of a star's light when a planet passes in front of it as seen from Earth, blocking a tiny fraction of the star's light, typically less than 1%, but detectable with precise instruments. NASA's Kepler Space Telescope, launched in 2009, revolutionized the field by using the transit method to survey a single region of the sky continuously for more than 4 years, monitoring the brightness of over 150,000 stars and discovering more than 2,700 confirmed planets and thousands more candidates awaiting confirmation. Kepler's mission revealed that planets are common, that most stars have planets, and that planetary systems come in an astonishing variety of configurations. Some systems resemble our own, with small rocky planets close to the star and gas giants farther out, but many do not. Some have multiple planets packed tightly around their stars, all orbiting closer than Mercury orbits the Sun. Some have planets in highly elliptical orbits, swooping close to their stars and then swinging far away. Some have planets orbiting binary stars, where 2 stars circle each other and the planet circles both, experiencing double sunsets like fictional world of Tatooine from Star Wars, except these worlds are real. Among the thousands of known exoplanets are many that challenge our understanding and expand our sense of what a planet can be. There are hot Jupiters, gas giants orbiting so close to their stars that their atmospheres are heated to thousands of degrees and may be slowly evaporating away. There are super-Earths, rocky planets, larger than Earth but smaller than Neptune, a type of planet that does not exist in our solar system but appears to be common elsewhere. There are mini-Neptunes, planets with thick hydrogen and helium atmospheres surrounding rocky or icy cores. There are lava worlds, rocky planets orbiting so close to their stars that their surfaces are molten. There are rogue planets, worlds that do not orbit any star but drift through the galaxy alone, ejected from their birth systems by gravitational interactions or formed in isolation. And there are planets orbiting pulsars, the rapidly spinning remnants of dead stars, somehow surviving the supernova that destroyed the original star or forming from the debris afterward, a testament to the resilience of planetary systems. One of the most exciting aspects of exoplanet research is the search for planets that might be habitable, worlds where conditions could allow liquid water to exist on the surface, because water is essential for life as we know it. The habitable zone, sometimes called the Goldilocks zone, is the range of distances from a star where temperatures are not too hot and not too cold for liquid water, and many exoplanets have been discovered within the habitable zones of their stars. Some of these are rocky planets similar in size to Earth, and a few orbit stars similar similar to the Sun, making them particularly intriguing targets in the search for life. One such planet is Proxima Centauri b, a rocky planet orbiting Proxima Centauri, the closest star to the Sun, located just over 4 light-years away. Proxima Centauri b orbits within the habitable zone of its star, and though the star is a red dwarf, smaller and cooler than the Sun, the planet's proximity to the star, about 7.5 million kilometers compared to Earth's 150 million kilometers from the Sun, means it receives a similar amount of energy. Whether the planet actually has liquid water, an atmosphere, or any conditions suitable for life is unknown, but its proximity makes it a prime target for future observations and, perhaps someday, interstellar probes. Another intriguing system is TRAPPIST-1, a red dwarf star located about 40 light-years away, around which 7 Earth-sized planets orbit, all of them packed into orbits closer than Mercury's orbit around the Sun. 3 of these planets orbit within the habitable zone, and detailed observations with the James Webb Space Telescope are underway to study their atmospheres, if they have any, and search for signs of water, methane, or other molecules that might indicate habitable conditions or even biological activity. The presence of biosignatures, chemical markers that might indicate the presence of life, would be one of the most profound discoveries in human history, fundamentally altering our understanding of our place in the universe. Detecting life on an exoplanet is extraordinarily challenging because the signals are faint and ambiguous. Even if a planet has an atmosphere, detecting it requires observing the planet's light separately from the overwhelming glare of its star, typically done by analyzing the star's light as it passes through the planet's atmosphere during a transit, a technique called transmission spectroscopy. Different molecules in the atmosphere absorb specific wavelengths of light, leaving characteristic signatures in the spectrum, and by carefully analyzing these signatures, astronomers can determine the composition of the atmosphere. Detecting oxygen, for example, would be significant because large amounts of oxygen in an atmosphere are usually produced by photosynthetic life, at least on Earth, though there are also non-biological processes that can produce oxygen, so caution is required. Detecting multiple biosignatures together, such as oxygen and methane, which react with each other and would not persist in an atmosphere unless continuously replenished, would be much stronger evidence. The James Webb Space Telescope, with its powerful infrared capabilities, is the first telescope capable of detecting molecules in the atmospheres of small rocky exoplanets, and early results are already providing insights into the diversity of exoplanet atmospheres, even if clear biosignatures have not yet been found. Beyond the search for life, exoplanet research is revealing the processes by which planets form and evolve. Planets form in disks of gas and dust around young stars, with dust grains colliding and sticking together to form larger clumps, which grow through accretion into planetesimals, which collide and merge to form protoplanets, which eventually become full-fledged planets, all while interacting gravitationally with each other and with the gas in the disk, causing migrations and dynamical instability that can reshape the architecture of the system. NASA's missions have observed protoplanetary disks around young stars in exquisite detail, revealing gaps and rings that indicate where planets are forming, offering snapshots of planetary systems at different stages of development and allowing astronomers to test models of planet formation. One surprising finding is that many planetary systems are more tightly packed than our own, with multiple planets orbiting close to their stars in resonances, where the orbital periods are related by simple ratios, such as 2 to 1 or 3 to 2, indicating that the planets have influenced each other's orbits through gravitational interactions. These resonant systems are stable over billions of years, but suggest a complex history of migration and interaction during the formation process. Our own solar system, with its wide spacing and lack of super-Earths, may be somewhat unusual, or at least not representative of the most common type of planetary system, a realization that has prompted astronomers to reconsider what is typical and what is rare. As you rest here, imagine the sheer number of worlds that exist, each one real, each one a place, though none of us will ever visit them. Imagine planets with red skies, orbiting dim red dwarf stars that burn for trillions of years, far longer than our sun will last. Imagine planets with rings more spectacular than Saturn's, or planets covered entirely in water with no land, deep global oceans that might hide life in their dark depths. Imagine planets orbiting binary stars where the sky holds 2 suns, where eclipses happen in complex patterns, and where the seasons are driven by the changing positions of both stars. Imagine rogue planets drifting through the darkness between stars, their surfaces frozen, their interiors perhaps warmed by radioactive decay or tidal heating from moons, solitary worlds with no star to light their skies. All of these worlds exist somewhere in the galaxy, and many of them are not hypothetical, but observed, catalogued, studied, though only as points of light or dips in brightness or wobbles in starlight. We cannot yet see the surface of an exoplanet, cannot yet resolve continents or clouds, but we are beginning to characterize their atmospheres, measure their sizes and masses, and determine whether they are rocky, gaseous, or something in between. In the coming decades, new missions will push these capabilities further. The search for life beyond Earth, once the domain of science fiction and speculation, is now a rigorous scientific endeavor, guided by data and driven by the same curiosity that has always led humans to explore. And whether or not we find life on another world, the discovery that the universe is full of planets, that worlds are as common as stars, that the cosmos contains trillions upon trillions of places where matter has gathered into spheres orbiting suns, is itself a profound revelation, expanding the stage on which the story of the universe unfolds. Now, as the journey through these discoveries draws to a close, as your breathing deepens and your thoughts begin to fade into the soft embrace of sleep, it is worth pausing to reflect on what all of this means. Not just the facts and figures, not just the distances and temperatures and compositions, but the deeper questions that NASA's work has helped us ask and begin to answer. For thousands of years, our ancestors looked up and wondered, and now we have answers to some of their questions, though each answer has led to new mysteries, new horizons, new wonders. We have learned that the universe is unimaginably vast, that the distances between stars are so great that light, the fastest thing in the universe, takes years to cross them, and that the distances between galaxies are greater still, measured in millions and billions of light years. We have learned that the universe is old. Nearly 14 billion years have passed since the Big Bang, time enough for stars to be born and die and be born again. Time enough for the first simple atoms to be gathered into stars and fused into heavier elements, scattered by supernovae and gathered again into new stars and planets and eventually into living things. We have learned that our solar system, once thought to be unique, is one of billions in our galaxy alone, and that planets are not rare but common circling most stars, coming in varieties we never imagined, challenging our definitions and expanding our sense of what is possible. We have learned that some of these worlds, cold moons orbiting giant planets, hide vast oceans beneath their ice, and that these oceans might be habitable, that life, if it arose there, might have been thriving for billions of years in darkness and isolation, independent of sunlight, a second genesis that would prove we are not alone. We have learned that stars are born in vast nebulae, clouds of gas and dust that collapse under their own gravity, and that they die in various ways, some gently shedding their outer layers to form beautiful planetary nebulae, others exploding in supernovae that briefly outshine entire galaxies and scatter the heavy elements necessary for life across the cosmos. We have learned that black holes, once theoretical curiosities, are real and common, that they lurk at the centers of galaxies, shaping the evolution of those galaxies, and that their gravity is so strong it warps space-time itself, creating regions from which nothing, not even light, can escape. We have learned that the universe is not static but expanding, that galaxies are moving away from us and from each other, and that this expansion is accelerating, driven by something we call dark energy but do not understand. We have learned that most of the universe is invisible, that the ordinary matter we are made of, the matter that makes up stars and planets and everything we can see, is only a small fraction of what exists, the rest being dark matter and dark energy, components we can detect only through their gravitational effects, mysteries that remain unsolved. And we have learned that the universe is full of surprises, phenomena that do not fit neatly into our theories, signals that arrive without explanation, structures that challenge our assumptions, reminders that for all we have discovered, there is still so much we do not know. These discoveries have been made possible by human ingenuity, by the collective effort of thousands of scientists, engineers, and visionaries who have dedicated their lives to exploring the cosmos, by the development of technologies that extend our senses far beyond their natural limits, telescopes that see in wavelengths invisible to the human eye, spacecraft that travel for years to reach distant worlds, computers that process vast amounts of data to reveal patterns we could never detect on our own. NASA and space agencies around the world represent the best of what humanity can achieve when we work together toward a common goal, when we set aside our differences and focus on the shared quest for knowledge and understanding. But beyond the facts and the technology, beyond the missions and the data, there is something deeper that these discoveries offer us. They give us perspective. They remind us that Earth, for all its beauty and importance to us, is a tiny world, one planet among billions, orbiting an ordinary star in an unremarkable region of an average galaxy, itself one of trillions of galaxies in the observable universe. This perspective can be humbling, but it can also be liberating. It frees us from the illusion that we are the center of everything, that the universe was made for us, that our local concerns and conflicts are of cosmic significance. It reminds us that we are part of something far larger and older than ourselves, that the atoms in our bodies were forged in the cores of dying stars, that we are, quite literally, stardust, the universe made conscious, able to look back on itself and understand, at least in part, where it came from and how it works. This realization, sometimes called the cosmic perspective, has the power to change how we see ourselves and each other. It reveals that the things that divide us, the borders and ideologies and differences that seem so important, are arbitrary and temporary, that from space, Earth has no borders, only continents and oceans and clouds, and that all of humanity shares this one small world, the only home we have ever known. It suggests that our survival and flourishing depend on cooperation, on caring for our planet and each other, on looking outward together rather than turning inward in fear or conflict. And it inspires a sense of wonder, a recognition that the universe is far stranger and more beautiful than we can fully comprehend, that every answer leads to new questions, and that the quest for understanding is never finished. As you lie here now, on the edge of sleep, let these thoughts settle gently in your mind. You are part of this story, part of the long chain of curiosity and exploration that began when the first humans looked up at the night sky and wondered. You are connected through an unbroken thread of atoms and energy and time, to the Big Bang itself, to the first stars, to the nebulae where new stars are born, to the planets that circle distant suns, to the galaxies that swirl through the darkness. You are made of the same matter, subject to the same laws, part of the same unfolding cosmos. And in this moment, as your breathing slows and your body relaxes, you are at peace, cradled by a planet that has sheltered life for billions of years, warmed by a star that will shine for billions more, surrounded by a universe so vast and ancient that your worries and fears shrink to nothing in comparison, not because they do not matter, but because you are held by something larger, something that has been here long before you and will continue long after, something that is both indifferent to your existence and also, paradoxically, intimately connected to it, because you are not separate from the universe, you are part of it, a brief flowering of consciousness in an ocean of space and time, aware, curious, capable of wonder. The discoveries we have explored tonight, from the footprints on the moon to the hidden oceans of icy moons, from the birth of stars in glowing nebulae to the death of stars in black holes, from the billions of galaxies scattered through space to the thousands of planets orbiting distant stars. All of these discoveries are gifts, pieces of knowledge hard-won through effort and ingenuity, offered freely to anyone willing to look and listen. They do not provide simple answers or easy comfort. They do not tell us why we are here or what we should do. But they do remind us that we live in a universe full of beauty and mystery, a universe that rewards curiosity, a universe that is, despite its vast indifference, also a place where wonder is possible, where meaning can be found not in being the center, but in being connected, in recognizing that we are part of a story far larger than ourselves. So rest now. Let the weight of these discoveries settle lightly on you, not as a burden, but as a blanket, warm and comforting. Let your mind wander among the stars, visiting worlds you will never touch, imagining oceans you will never swim in, tracing the paths of light that have traveled for billions of years to reach your eyes. Let yourself feel small in the best way. Small, but part of something infinite, temporary, but connected to something eternal. And as sleep comes, as the thoughts fade and the images blur, know that the universe is still there, still turning, still unfolding its story, and that somewhere in that vastness, on a small blue world orbiting a yellow star, you exist, you wonder, and for this brief moment, that is enough. The stars will still be there tomorrow, the galaxies will still be spinning, the planets will still be orbiting, and NASA will still be exploring, sending its machines farther into the darkness, capturing new images, making new discoveries, adding new chapters to the story that began when the first conscious being looked up and asked, "What if?" And you, when you wake, will still be part of that story, still connected, still capable of wonder, still able to look up at the night sky and feel the pull of curiosity, the quiet thrill of knowing that we have only just begun to understand the universe we inhabit. For now, though, let it all go. Let the Moon and Mars and Jupiter and Saturn, let Europa and Enceladus and Titan, let the nebulae and galaxies and black holes, let the exoplanets and dark matter and cosmic mysteries, let all of it fade into the background as sleep comes, gentle and inevitable, carrying you away into dreams where perhaps you will fly among the stars, weightless and free, or perhaps into deeper sleep where even dreams dissolve into peace. Either way, you are safe, you are held, and the universe, vast and strange and beautiful, continues its slow dance through time, indifferent and magnificent, waiting for the next moment of wonder, the next discovery, the next question asked by minds like yours, reaching out from a small world toward the infinite, seeking not to conquer or control, but simply to know, to understand, to be part of the great unfolding mystery. Sleep well, traveler. The cosmos will be here when you wake.